So, I hope you have tried it on your own, because it will be important for solving some assignments and also for the final exam, because there may be some problems related to this, and as you would have, if you tried it out, you would have realized that it is a really straightforward and simple problem. I have already mentioned it earlier also. So, now let us see, if in case you have not tried it out, what goes on here. So, if we have something like this, we know that this B and E are for the dislocation onto which the stress has to be calculated, sorry, the force has to be calculated. So, this is 0 0 1, meaning epsilon 1 and 2 terms will go away. So, this term will go away, this term will go away, this will go away, this will go away. What we will remain with is this one and this one. So, F z is automatically 0 here. What more? We will have B Berger vector equal to 0 0 1. Now, here B 1 B 2, here B 1 B 2, these two terms will go to 0. So, what we are remained with is sigma 2 3 B 3, and assuming there is a line vector, so I will write it 3, and sigma 1 3 B 3 epsilon 3 and 0, which means this is f x by L, this is f y by L, this is f z by L. And what we see is that f z by L is 0, which should not be surprising, because this dislocation is a line and there cannot be any force in the normal direction. So, the z direction force is 0. What we have are only f x by L and f y by L. So, we can see these are the quantities, but that is not still the complete picture. Let us now look more closely. We have said that this particular dislocation is a edge dislocation. Now, if you remember, what is the form of stress for a for a edge dislocation? So, the stress dislocation is sigma x x, sigma x y 0, sigma y x, sigma y y 0, 0 0, sigma z z. Now, where is the sigma 2 3 component here? This should have been sigma 2 3, this should have been sigma 1 3, and these are 0, which means that this is also 0, this is also 0. So, the overall force is 0. So, all this exercise is telling us that the force because of edge dislocation onto a screw dislocation is 0, and again this should not be surprising, because if you remember, the components, stress components of edge dislocation matrix are in effect in a way inverse of the stress components present in the screw dislocation. So, these stress components do not influence the screw dislocation, and therefore, what we have obtained is what we should have expected from the very beginning, that edge dislocation cannot apply any stress onto a screw dislocation. And in fact, we can now extend this to find out what will be the forces because of a screw dislocation onto a screw dislocation. But but before that, this is the expanded way to solve it. We could have also solved it in a more compact manner, because we already know sigma and B. So, you could have said that so sigma here is sigma x x, sigma x y and 0, sigma y x, sigma y y 0, 0 0, sigma z z. So, sigma dot B, where B is equal to 0 0 1, if you remember. So, sigma dot B will come out to be 0 0 sigma z z, and when you multiply it with sigma dot B cross E, now what is E? E is also equal to 0 0 1. So, we have 0 0 1 cross multiplied with 0 0 1 kind of vector, and what should be the result? Yes, that should be equal to 0. So, the previous method was where you used the expanded form and you looked at all the parameters. This is a more compact way to solve it, because you already know the sigma is arising because of which particular dislocation. So, you write it in this form, then you know that what is the Berger vector. So, this is 0 0 1 and you can quickly get to this form of the equation. Sorry, sigma dot b will condense to this form, and then sigma dot b cross E you will say okay. So, this is sigma dot b cross E is equal to 0. Okay, so, now coming to the next part of the question, which I said was to calculate force on screw dislocation, and we will assume again the same Berger vectors and line vector. Due to another screw dislocation. So, this is completely new thing. So, now we are trying to calculate force on screw dislocation because of screw dislocation. So, see what all we have done. We have looked at force on edge dislocation because of edge dislocation. In the example, we looked at force on screw dislocation because of edge dislocation, and now third we are looking at force on screw dislocation because of another screw dislocation. And for this also we are given line vector is equal to 0 0 1. The Berger vector I am not giving, but if the line vector is given like this, then the Berger vector will be either 0 0 1 or 0 0 1 bar. So, it can be one of the two, meaning it will be b or minus b. So, again the expanded form of it, you can look at this relation and say okay, I have, it will be something similar to this, because here I have assumed all the sigma components, and only thing that I am assuming is that epsilon 3 is 0 0 1 and b is 0 0 1 form, and therefore, it will come out to something like this. So, you can directly come and say it will be sigma 2 3 b 3 sigma 1 3 b 3 0. So, that is the advantage of using the expanded form. You can directly arrive at the solution, or if you do not remember the expanded form, then you know that sigma dot b, sigma over here, this is because of screw dislocation. So, this is like this. So, I am interchangeably using 1, 2, 2, 3 kind of subscripts and x, y, y, z. So, you will have to bear with me on that, but you must you should be able to directly relate. When I say 3, it means z, 2 means y, and 1 means x. So, this is sigma, and when you multiply it with b, which is 0 0 1, what you get? And then you multiply it with then you will get sigma 2 3 b 3 sigma 1 3 b 3 0, which is same as saying sigma y z b, because b is the Berger vector we have, sigma x z b and z. So, we know this is f x by L, this is f y by L, this is f z by L. So, again we know that we can see that f z quantity has come out to be 0, which is expected. F x and f y have come out to be this form. Now, we can use the sigma y z that we already know for a screw dislocation. So, we can write here I will write B1, B2, where B2 is 0 0 1 and B1 is either 0 0 1 or 0 0 1 bar. Why? Because we know this is arising from the Berger vector, because of which stress is being created, and that for which we are only given line vector 0 0 1. So, here only we know that B is either 0 0 1 or 0 0 1 bar. So, you have to be clear about this part, and then you can write 2 pi by x square plus y square. Now, assuming that both of them are of same sign, meaning what we are saying, if we are saying that both of them are right handed screw, so here assuming that both of them are same of the same sign, then this relation would become GB square, where B we have already taken to be 1. So, it becomes 1, or let us put it GB square by x by 2 pi x square plus y square, and f y by L is equal to so, this is the climb because it is F y, this is the glide, but only in terms of edge dislocation. This climb is does really have any meaning. Now, here looking at this, we are looking only at numbers, and but if you want to put it qualitatively what it means is that f x by L is repulsive. So, this comes out to be positive, which means that the two dislocations are trying to move apart. So, the f x by L is repulsive for screw dislocations of same sign. So, okay, here I have not mentioned, but we assumed same sign. What does it mean? Same sign meaning B 1 equal to B 2 equal to B. And if one of them were opposite sign, then it will become minus B square. So, f x is now minus, meaning it is trying to move closer to each other. So, f x by L will become attractive for screw dislocations of opposite sign. So, we have looked at various combinations of stresses arising from different sources, edge dislocation, screw dislocation, acting on edge dislocation and screw dislocation. One combination that you can try and solve it using this is what will be the effect when you have stress field being generated because of a screw dislocation and its effect on edge dislocation. So, this is one example that we did not solve, and I leave it to you to solve it. What you need to do is again calculate the stresses because of the screw dislocation. You are given x and y, just look at the sigma dot b cross E form. So, here you can again take E along 0 0 1 for both of them. The Berger vector for this for the screw dislocation is along the line direction, which will be 0 0 1 or 1 0 0, and for this you can take it along the perpendicular direction. So, the Berger vector would be like this. So, to simplify, which would mean that if the line direction is 0 0 1, the Berger vector has to be x y 0 form, and to simplify it you can make it either x 0 0 or 0 y 0. So, that is something you can do without loss of generality and find what should be the f x by L and f y by L onto the screw dislocation. And remember that what we earlier found was that for this configuration f x, in fact all the f was equal to 0. So, compare this force with the force value that you obtain over here. Do we still get 0 or do we get something different? So, I will leave that to you and we will go on to solve still another example. Now, this time it will not be related to action of forces, this time we will be looking at the slip planes. So, you saw that we found that there are certain kind of slip planes that are possible. So, this next example and one of the system which is simplest to begin with for understanding this slip planes we have already talked about is FCC. Why it is simpler? Because there are unique, not unique, but only one set of directions, one set of planes and one set of directions. Okay. So, in this particular problem you are given that you are given that a dislocation moves it is originally like this, then it moves like this. We will talk more about this what is called as cross slip, but right now just to understand different planes I am giving you this problem and then it moves into this plane. Although the picture may show that these two are parallel, but you do not need to assume that. Okay. And what you are given additionally is that this is 1 1 1 plane. Now, if this is 1 1 1 plane, you are asked what are the possible planes, this one P 1, what are the possible planes P 2, and simultaneously if this is P 1 what will be U 1 which is the line vector, and if this is P 1 this is what will be this one U 2. So, if you remember which particular dislocation can really cross slip, it is only screw dislocation, but we are showing a mixed dislocation here. So, do not worry about it, we will explain you what the phenomena later on, but just assuming that it is only the screw dislocation which has cross slipped from plane P 2 onto 1 1 1 plane and then 1 1 1 plane to P 1. You have to tell us what will be the Berger vectors or sorry the line vectors over here and what will be the corresponding planes. So, you can assume as I said screw dislocation. It will make our job much more easier when you assume screw dislocation. So, the first thing that you would realize now that I have already given you the hint that it is a screw dislocation, you should realize that whatever be the U 2 that will also be the Berger vector or at least the plus or minus of that Berger vector. So, Berger vector has to be plus minus U 2, Berger vector has to be plus minus U 2. Next, if this is a plane 1 1 1 and this is a plane 1 1 1, then sorry this is also another plane of this family 1 1 1, then another thing is that whatever is the Berger vector, this particular Berger vector has to be common to both the planes. So, first let us see what are the possible different 1 1 1 planes. So, 1 1 1 can be written as 1 1 1, it is negative 1 1 1, 1 1 bar 1 or bar 1 bar 1 1. So, basically there are 4 different 1 1 1 planes. So, the P 1 and P 2 can either of these 4 different planes or it is negative. So, the possibility for planes are like this. So, now I will have to write it can be if it cannot be 1 1 1 because 1 1 1 is this one and it is moving on to another plane. So, the other planes possible are 1 1 bar 1 or 1 bar 1 1 or bar 1 1 1. So, these are the 3 possibilities and corresponding to each of these we know there is also a negative. So, this which is not really unique, but for the sake of completeness we will list it out over here. So, either this or this, this or this, this or this, these are the 3 possibilities for plane. If this is the possibility for plane, what will be the common direction? So, if this is 1 1 bar 1 and other one is 1 1 1, what is the common direction which is of the type 1 1 0? And as you will see, as you will find out, there is only one possibility here. So, in this particular case it will be, so you can see this particular one will lie on this because you can take a dot product, it will come out to 0. If you take a dot product with this, it will come out to 0. For this one it will come out. So, again dot product of these two will be 0, dot product of this with 1 1 1 will also be 0. The third possibility of u is so, again if you take the dot product of 0 bar 1 1 with bar 1 1 1 is it is 0, 0 bar 1 1 dot product with 1 1 1 which is the other plane will be 0. Why we are taking dot product again to remind you, because dot product tells us that this lies in this plane 1 1 1 plane. If this particular direction lies in this plane, then this has to be the dot product must be 0, and we said that this is a common line which is on both of these. So, it should be dot product for both of these should be 0 and that is what we are getting, and these are the only if P is 1 1 bar 1, this is the only possibility in this set of directions. If P is 1 bar 1 1, then the common line vector of this type 1 1 0, there is only one possibility bar 1 0 1. If bar 1 1 1 is the plane, then this is the only possibility for this direction, and therefore, we have these possible sets of P and U. So, for corresponding to this P, this is the only possible U. If this is the P 1, this is the only possible U 1. If this is P 1, this is the only possible U 1. And just like in this particular case, there are negatives. So, here also you will have negative, which we can write as so these are not really additional planes, but just the negative of these. So, I have written over here. Similarly, so now this is corresponding to for each corresponding plane we have found a one u direction. Similarly, for each P there will be one u direction. So, one of these, it will not be anything outside this. So, what we are saying is that P and U are related, P1 and U1 related, P2 and U2 are related. Both of them can be same, both of them can be different. If it is the same screw dislocation with the same Berger vector, then what do you think would happen? Then this will have to, this U2 will have to be equal to U1, because the, and we already know that the Berger vector does not change. Therefore, what it implies is that P1 must be equal to P2. It also implies that U1 must be equal to U2. So, although we began with the assumption that P1 and P2 need not be same, but we see that since Berger vector is same, which would mean that this line vector has to be same, and therefore, this remains constant, and therefore, this again P1 and U2 U1 combination will also be same as P2 and U2. So, this can be, this P is now either P1 P2, U is U1 U2. Hence, we are now in a position to describe the different two different planes and two different directions. So, now we have looked at several examples, and it is time that we come back to little bit more understanding about dislocations and slips. So, in this context, let us come back to our some fundamental understanding what we studied in our mechanical behavior course, if you have taken that, and what is called as critical resolved shear stress. So, let us try to understand this concept, critical resolved shear stress. So, this is let us say a single crystal, and there must be a certain particular plane. So, let us say if this is FCC, there will be a certain 111 plane onto this. So, let us say this is one particular 111 plane, there will be more than one. If you remember, there are 4 different planes. So, there can be 4 different planes, 111 planes over here. Let us say this is one particular plane that we are talking about, and in fact, you should be talking about all the plane, but for the sake of understanding we will limit ourselves to one particular 111 plane. And let us say we have a dislocation which is like this, and for this dislocation this is the slip direction, and for this particular plane this is the normal. So, this normal is oriented at some angle theta to the axis, and the slip direction is oriented at some angle lambda. Now, what you need to understand here is that that theta plus lambda is not equal to 90 degree necessarily, meaning in some particular instance it can be possible, but it need not be theta plus that theta plus lambda has to be 90 degree, nor independently nor lambda has to be 90 degree necessarily. So, these two are something which whenever we draw something like this, we end up believing that theta plus lambda has a relation, and similarly or lambda has a relation with this axis, but that is not true. Now, let us say that there is some force acting onto this in this particular direction, which will cause the dislocation motion, and the area is A, because of which we can say the stress onto this is sigma. So, a stress sigma is applied, or you can say a force F is applied onto a area A. Now, this stress would should cause the motion of the dislocation, and in effect this is what will lead to the strain, the overall accumulation of such the movement of such dislocations would lead to strain, which we will again see later on. But for now let us say this is the force acting onto it. Therefore, we can say that onto this particular plane, which is the plane onto which the dislocation lies, the resolved shear stress is equal to F by A cos phi cos lambda. You would be able to, you should be able to see that directly, and there is, it is not very difficult to come to this conclusion that the resolved shear stress acting onto this particular plane because of this acting force F by A is F by A cos phi cos lambda, and we have already said that F by A is sigma cos phi cos lambda. So, the shear stress acting onto this plane is equal to sigma cos phi cos lambda. So, earlier you remember we were able to relate the stresses to the forces, and but we never said how to resolve the external stresses to the stresses onto the plane. This is what this particular relation is telling us, and as you can see that it is not so difficult, it is very easy to find out what will be the resolved shear stress. So, this is resolved shear stress. Now, what is this minimum resolved shear stress? How much should be this stress for it to be able to move? That is called a critical resolved shear stress. We will come to that particular topic in the next class. You in the meantime try to prove that the resolved shear stress is equal to sigma cos phi cos lambda, and we will see you in the next class.